right, well, here we go with our next topic, and that is going to be vectors. So here we get a little bit of trigonometry thrown in with the algebra that we've been using so far. And this is a little bit of a review from the summer assignment as well, but let's talk about it a little bit here. Vectors are going to involve arrows, and we're all familiar with arrows. There goes one now. Woo! All right. So these are going to be representations where we are using arrows to represent things. So just for fun, draw an arrow, or think about drawing an arrow anyway. And if you did do that, you could measure how long the arrow was. So maybe we're going to measure in centimeters. So how many centimeters is that? Well, that's great. Now you have an arrow that's a certain number of centimeters. What good does that do us? Well, how about if we said that every centimeter is equal to 20 miles? Now you've got an arrow that represents something a little bit different than just an arrow that's a few centimeters long. You have a scale model here, and question to ask maybe would be how might this be useful? And I'm sure you have some good ideas already. If you've ever looked at a map, you know it's a scale model diagram. That's not the actual size of the entire planet, it's a scale model diagram. And similarly, that's not the entire tri-state area there. And that's not the entire lower Manhattan. We have scale model diagrams, and those can be useful in lots of different ways. Now, also in terms of engineering, let's say, I guess you could be, if you're a landscape engineer, you might want to draw the things out to scale before you start making some big moves. Or if you're designing a house, the blueprints are scale model diagrams, and I'm sure you're familiar with these ideas. Building an automobile, we're not going to just go out and build it, going to plan the thing out pretty well beforehand, and these scale model diagrams can be a really powerful way of doing that. Okay, so our vectors are going to be scale model arrow representations of physical quantities, things that we talk about in physics. These vectors, like an arrow, are going to have size to them, and like an arrow, they're also going to point in a particular direction, and that becomes important for us. Okay, so if we just have the size of it, they call that a scalar. So a little vocabulary word for you there. Just the size would be the scalar. But when you add in the direction, you also have what we call a vector. So direction, north, south, east, and west is a way that we could be talking about directions. The lines in the middle there between north and east would be called northeast. And the line in between north and west would be northwest and southeast, of course. Another way that we're talking about direction, and we have been talking about direction and will continue to, is using positives and negatives to talk about the direction. Okay, so all right, so you were going to use the positive and negatives. It looks like it might be cut off a little at the bottom of the screen there, but positives and negatives for direction as we've been doing. So northeast, southeast, northwest, southwest, that's pretty good for those four directions. But we want to be able to talk about any directions at all, and here is another way of notating that. 30 degrees north of east is a way that we do it, and that should be read as 30 degrees toward the north from the east. So here's a diagram to illustrate that for you. 30 degrees north of east, we would all agree, is in this direction here, 30 degrees toward the north from the east. So we'll all be on the same page with that convention there. Okay, so vector addition. That's going to be a big part of what we're doing, adding physical quantities together, adding two or more vectors together. And the resultant is going to be one vector that sums up these additions. So we had two or more vectors going on. What's one vector that represents what's going on? So, for example, if you had somebody going 2 meters to the east and then 3 meters to the east, we could represent that with arrows, and we could use what's called a head-to-tail vector diagram. And head-to-tail means you play out one of the vectors, and wherever it ends up, the head of that one becomes the tail of the next vector. Let me illustrate that here. So 2 meters to the east plus 3 meters to the east. There's 2 meters to the east. There's presumably 3 meters to the east. And in red here, I have the resultant that is the addition of the two. So there's the head to tail diagram, 5 meters to the east. Now we could do this for any number of vectors in any number of directions. I'll use some pretty straightforward examples here to get us started. So if we had a head-to-tail diagram of 10 meters to the north plus 5 meters to the south, you've probably already figured out what the result of this is going to be. But let me just show you in a head-to-tail diagram. There is my 10 meters to the north. There is my 5 meters back to the south. You can see it's a head-to-tail diagram. And the resultant is always from where I started to where I ended up. So there's my resultant in red. And as you probably already guessed, that would be 5 meters to the north. So there we go with very simple head-to-tail diagrams. And again, you could do this as complicated as you want with these head-to-tail diagrams. And they're useful for kind of showing where the resultant is going to be, what we're after. Okay, so what's the resultant of 3 meters plus 4 meters? Do you know? Have you got it figured out? Well, it's a trick question, right? Because there's no directions. 3 meters and 4 meters, I don't know what's going on. But if I tell you 3 meters this way, and then maybe 4 meters going this way, now you have something to go on. Again, I could have had the 3 meters and the 4 meters going in any number of directions. But I want to illustrate here the example of when we're working at a 90-degree angle. So a little bit of right angle trigonometry. So we're talking about the Pythagorean theorem, and you know it probably from your math classes that a squared plus b squared is equal to c squared. And what is that side opposite the 90-degree angle? So I've got the 90-degree angle over here. I'm representing it as c. Oh, there's Mr. Goodall reminding us of some things here. All right, so that side c, what is the name for that side c? Well, that is, using the Pythagorean theorem, that side opposite the 90-degree angle, figured out by Pythagorean there. He came up with a name for it, and that was the hypotenuse. You probably knew that already. And here's a comical representation of the idea of coming up with that word hypotenuse. How about that? Okay, so let's see. So what's the resultant of 3 meters east plus 4 meters to the north? Well, it turns out it's going to be 5 meters. Did you already know that from right angle trigonometry, that this is a 3, 4, 5 triangle? Hey, watch this. I'm going to turn the lights on. How's that? Any better? All right. So the magnitude is 5 meters. Did you already guess that? And how about the direction? The direction, you would end up using the inverse tangent to figure that out. And that would give you an angle of 50 degrees toward 53 degrees to the north of east. Let me see if I can do a little bit better job of doing that by drawing a scale model head-to-tail diagram. Now, I'm not always going to draw scale models, but I want to illustrate this for you to show you that if you did do a carefully drawn out scale model diagram, you would get a result that worked out pretty well that would back up the trigonometry. Let's see what I'm talking about. So for that example, I'm using a scale here of 2 centimeters is equal to 1 meter. So my 3 meters to the east is going to be represented by a 6 centimeter long arrow. And similarly here, I'm going to add in my 8 centimeters going up to the north to represent my 4 meters. And with my ruler here, and I did it carefully, and you can try it at home as well, I measured out my resultant. My resultant is this arrow over here. It's from where I started to where I ended up on my head-to-tail diagram, and sure enough, it measured out to 10 centimeters, which gives me my 5-meter answer. Now, of course, I can do that with the Pythagorean theorem as well, because the square root of 3 squared plus 4 squared is equal to 25 is what it's going to come out to. And the square root of 25 is going to be 5. So that's how I did that. Now, since the tangent is the opposite over the adjacent, I took the side opposite, the 4 meters, and divided it by the adjacent side, and I took the inverse tangent, and that gave me the 53 degrees, and my diagram shows me that it's 53 degrees to the north of east. So that's how that worked out. Okay, so right triangles are pretty straightforward. If we were talking about why we might want to be doing all this stuff in the first place, there are all kinds of applications now for this. Originally, they just figured out the math of it, and then later on found out that this could be applied to physical quantities to make some pretty good predictions. So this can be used for GPSs. Well, I had a professor who was in bombing runs in World War II. So he talked to us about the idea of making these vector calculations of the weight of the airplane, how the airplane would change when you drop the bombs, when you burn the fuel, how your fuel speed would be, the rate of burning fuel would be indicated by whether you were going into the wind, and when you're coming back, maybe the wind is at your back, or the wind is shifting maybe as you go. And he did say something that I thought was very interesting. And he said that you don't know pressure in solving this. And we all feel pressure on a test or something like that, right? So you don't know pressure until you're making these calculations and bullets are coming through the floor. Because when you are trying to drop bombs on people, they don't want you doing that. And interesting too, because no calculators and no computers. So with all that pressure trying to make those calculations, that always stuck with me. All right, so hurricanes, that's just another good thing for being able to take in all the different things that are going on and make some kind of predictions with the hurricanes. Not always accurate, but we're getting better and better at that. And this is an indication here of all the airplanes that are up in the sky at one time. And that takes a lot of vector coordination to keep all that going. Well, I am going to pause here and continue in a couple of minutes. The bell is ringing, it's time to go to class. All right, well, here we go. We're going to pick up with our discussion of vectors, pretty much where we left off, and talking about the practical real-world applications. Once again, to emphasize, that's what you should be doing all the time. Think about what I put in front of you and where it could go from there, because it's amazing places that the physics can go, and we're starting at the building blocks of it. But if you're already thinking where it's going to go, then you'll do better in this class. And also, as many of you said, you want to go on in engineering careers, now's a great time to start thinking along those lines. Okay, so here is another example of vector addition with a right angle. So try it. Try to draw yourself a diagram for this, and then try to come up with the resultant. Hit pause, and then come back and see if you got the right answer. Okay, are you back? How did you do? Well, here's my answer. Is that what you came up with? All right. Well, hopefully it is. And let's give another one a try here, too. Now I want to tie in the idea of the one-dimensional motion. We've got the idea here that this is going to be heading off at a particular speed in a particular direction. So now I'm asking you, how far does the boat travel? Okay, in 30 seconds. Why don't you pause and see if you can get the answer that I'm about to show. Was that what you got? 336 meters? All right, well, you're off to a good start then. Okay, here's another one that's at right angles. If you remember when I was talking about the idea of derived units, I mentioned newtons. So we're not really deriving the newton yet, other than what I've already explained to you. But here the N indicates a 15.0 Newton force. So with a 15.0 Newton force, and then we have a 30.0 Newton force acting in at a right angle to the first force. So anyway, just getting you used to the terminology of newtons here. But it works the same way for any physical quantities, and so your right angle trigonometry and your vector addition head to tail is going to work out very well. Give it a try. Hit pause, and then let's see if you have the right answer. And we're back. And here's the answer that I came up with. What is the resultant of the two forces? I came up with this answer here. How did you do? Hopefully, we're on the same page. If not, we can talk about it in class. Okay, let's see what I have in store for you here. All right, one more example here, just to make sure you really know what's going on. Here's another example of two vectors that are going to be at right angles to each other. So a little Pythagorean theorem. And watch pause and see how you do in finding the resultant velocity of the airplane. And we're back. And the answer is, there you go. All right, here I'm trying to keep with the correct number of significant figures. I'm not going to be a stickler for that, but worth pointing out from time to time. 50.0 indicates 3 significant figures. And yeah, so here I'm using 3 significant figures again. Okay, so now we're going to talk about resolution of vectors. Vector addition means that we're going to take one vector, add it to another vector to get a one vector resultant. So we're going to add a number of vectors together to get one vector that is the resultant. In resolution of vectors, we're going to take a vector and split it into 2 parts, or what we call components. So if you have a scenario like this one, 25 Newton force acting at 30.0 degrees north of west. My question is, what are the northern and western components of this force? What am I talking about? Well, I'm going to give you a diagram to represent this, and here it is. Well, first of all, here are the answers. So we're going to come up with these answers. Maybe even without the diagram, you know what to do. It is a trigonometry problem. But here's the diagram that I promised. Okay, so there is my vector that represents 30 degrees toward the north of west, and there's my 25 newtons, or 25.0 Newton magnitude. Okay, in red and green, reddish and green anyway, I'm drawing the components in the western and the northern direction. In green is the western component of that force, and then the part that goes to the north is in reddish color over here. So the green is adjacent to my 30-degree angle, and the red over here, the northern component, is opposite the 30-degree angle. So with a little bit of trigonometry, I can break these into its parts. Since the northern component is opposite the angle, I'm going to use the sine to find out what's going on in the northern direction. Turns out that the sine of 30 degrees is 0.5, so I'll have 12.5 newtons to the north. To emphasize what I've said earlier, you have to make sure your calculator's in degree mode, or you're going to get some answers that aren't going to make a lot of sense if you're in radian mode. Okay, the western component over here, since it is adjacent to the angle, will involve the cosine. So 25 multiplied by the cosine of 30 degrees gives me that western component that I showed you earlier. So there's the resolution of vectors. And we'll be using that a lot. The next thing that we're going to do is add some vectors that don't fit nicely into the nice Pythagorean theorem. They're not at right triangles. But it doesn't matter how complicated the vectors are, we can boil it down to right angle trigonometry. What am I talking about? Glad you asked. Let me proceed. Okay, so here is a person traveling at an angle, and then they're traveling at another angle. This you could draw out as a head-to-tail diagram, do it as a scale diagram, and you could carefully measure things out. Okay, but once you start adding a lot of complicated vectors, it's going to get tricky. The mathematics is the route you want to take, the trigonometry in this case. So here's what I'm going to do in looking for the resultant displacement. I'm going to take each one of these and do a resolution of vectors. Let me show you what I'm talking about. The first vector is 100 kilometers at 60 degrees south of west. So, actually here I tell you what the resultant is. This is the answer that we're going to end up getting, and I'm going to show you how we end up getting that answer. So 219 kilometers at 71.3 degrees south of east. Now let me show you how I did it. All right, so the first thing that I did is I took that first vector. It's 100 kilometers at 60 degrees to the south of west. So the western component is going to be adjacent. I'll use the cosine. So in the western direction, that first vector is 50 kilometers. Similarly, in the vertical direction, the southern direction in this case, I'm going to use the sine because the southern component is opposite the angle. So the sine is the appropriate trigonometric function. All right. Vector number 2 I can break down in a similar kind of way. It was 170 kilometers to the southeast. Well, southeast is right in the middle of the 90 degrees between south and east, so I will use the cosine of 45 degrees for the adjacent side and the sine of 45 degrees for the opposite side. So there is my second vector and my first vector broken separately into their horizontal and vertical components. Now, in the horizontal direction, the west and the east are working against each other. So the horizontal resultant, you could put it that way, I guess, or the horizontal component of the resultant is going to be 70 kilometers to the east, 50 kilometers to the west, but then back 120 kilometers to the east, netting me 70 kilometers to the east. In the vertical direction, they were both in the southern direction, so I'll simply add them together to come up with 206.6 kilometers to the south. Now, I'm not going to be perfect on these all the time. I'll probably slip up from time to time. But I am trying to do the best I can with the significant figures. Since my initial numbers certainly didn't have 4 significant figures, I'll round that to 207 in my next calculations. Do you see where I'm going with this? Because now I've taken these two more complicated vectors and I've broken them down to components, overall components, that are going to be at right angles to each other. And now I'm right back to my Pythagorean theorem and right in my comfort zone. So here we go. I am going to draw out my 70 kilometers to the east. Then I am going to do the 206.6 kilometers to the south, which I'm going to use in my calculation as 207. You'll see that in a moment. And my resultant is from where I started to where I ended up. So I am here. You can see here's where I converted it over to 207. 70 kilometers, 207 kilometers. There's my Pythagorean theorem that's getting me the 219 kilometers that I would have to call the magnitude. And then, since it's the opposite over the adjacent, I'm using the inverse tangent of 207 divided by 70, and that gives me 71.3 degrees toward the south of east, and here is my resultant. The same resultant that I showed you a little while before, but there's the work behind it. Well, I have one more thing to talk about with vectors, and we covered some good ground here already. Hopefully this is all comfortable to you. If not, we certainly can discuss it in class.